Now that we know how to calculate partial derivatives, it's going to make that old way of calculating implicit derivatives from Calculus 1 completely obsolete and unnecessary. The new way with partial derivatives is going to be so much simpler. But just for the sake of torturing you, I'm going to remind you of the old way. The term implicit derivative might seem familiar, but you might not remember what exactly I'm talking about. So let's look at the Calculus 1 method that you probably learned a few semesters ago for doing this. So we would have been asked to find dy dx for a function that's given to us implicitly. So let's say we've got x squared y plus 2x minus 3y equals 12. And we want to find dy dx. There are some functions that you can go through and solve for y. We could probably do it on this one. I wouldn't suggest doing that though. What we learned to do in Calculus 1 is to go through and differentiate everything in this function with respect to x. And you always assume that y is a function of x. Y is the dependent variable, the output variable, and x is the independent variable. So we just go through and we differentiate everything with respect to x, and we have to remember that y is a function of x. So this first term we see here, we've got to do with product rule. So I'm going to do the derivative of the first times the original second plus the original first, and the derivative of the second is the derivative of y, and we write that as dy dx. Because we don't know what y is equal to with respect to x, but if we did, we would take its derivative. So instead of taking its derivative, we just write the derivative notation saying the derivative of y goes in this spot. So that's the product rule for the first term. And then the derivative of 2x is just 2. The derivative for minus 3y is negative 3 dy dx. Anytime you take the derivative of a y, you've got to include dy dx. And then the derivative of 12 is 0. So we've gone through and we've differentiated everything with respect to x. And now we're going to move everything that does not have a dy dx over to the right-hand side, which means we've got to subtract the 2xy and we've got to subtract the 2. And we're doing this because I've got two terms here that have dy dx, and I want to solve for dy dx, which means I need to isolate them on one side and factor them out. So we're left with x squared dy dx minus 3 dy dx equals negative 2xy minus 2. Now we can factor that dy dx out on the left. And divide over the x squared minus 3 in order to solve for dy dx. So this was our Calculus 1 method for calculating implicit derivatives. These are implicit derivatives because of the way the function is presented to us. The function is given to us with all of the x's and the y's jumbled together. Obviously not a very technical math term. The most technical way to say that is a function is implicit if it is not solved for its dependent variable. So if we had this function given to us as y equals a function of x, that would be explicit. But we didn't. We had the y's and x's all jumbled together, which means it's implicit. So the opposite here of function is explicit. If it is solved for its dependent variable. And this is typically what we see as function notation, y equals f of x. This is explicit function notation. And up here, implicit, it is not solved for its dependent variable. So now that I've made you suffer through the old Calculus 1 method, we can actually use partial derivatives to get this implicit derivative much, much easier. So our new Calculus 3 method says any partial or implicit derivative that we're asked for, and it doesn't necessarily have to be the derivative of the output variable with respect to the input variable. We've got a lot more options now, especially now that we're working with functions of several variables. We could set up this derivative any way we want to, especially now that we're going to use partial derivatives to do that. But just for example, to base it on the one we just looked at, to do the derivative of y with respect to x, we're going to negate and flip that and use partials. So I'm going to say this is negative f sub x over f sub y. So f sub x means the partial with respect to x. And remember, f sub y means the partial with respect to y. So no matter what type of derivative you're asked to find, you can just negate it and flip it and use partial derivatives. So with this exact same function we just did, we had, let's see, x squared y plus 2x minus 3y equals 12. If we do it with the partials method, x squared y, and I've already forgotten it, plus 2x minus 3y. If we want to find dy dx using partial derivatives, we're going to do negative f sub x over f sub y. So I just want to go through and find the partial with respect to x. So I'm going to do 2xy plus 2. And on the bottom, I'm going to do the partial with respect to y, which is x squared minus 3. To make this match the one we had up with the Calc 1 method, though, we'll go ahead and distribute that negative in the top. So negative 2xy minus 2 over x squared minus 3. And is that what we got just a minute ago? Let's see. Negative 2xy minus 2. Negative 2xy minus 2 over x squared minus 3. Negative 2xy minus 2 over x squared minus 3. Exact same answer, so much less work. That took us probably 5 minutes to go through this whole Calculus 1 method of finding the implicit derivative. It took me probably 1 minute to do it with partial derivatives. So much easier now. We got the exact same answer. So let's look at another one. So this time I'm going to give you one function and we're going to calculate a couple of different derivatives. So let's consider the function x cubed plus 3x y squared minus 2yz cubed equals 5. And we're going to find a couple of things. The first one we are going to find is, since this is a function of several variables, these are going to be partial derivatives. I'm going to find the partial of x with respect to z. The partial derivative of x with respect to z. And I can do that if I negate it and flip it. So I don't want z in the bottom, I want z in the top. And I don't want x in the top, I want x in the bottom. So I don't have to think of this as an implicit calculus 1 derivative. I can do this with my regular old partial derivatives that we just learned if I negate it and flip it. So in the numerator, I want to put the partial derivative with respect to z. One thing that you should do, and I didn't do it on the last one, I probably should have, but it's not going to make a difference, is we should get this guy set equal to 0. It's not going to make a difference because it's a constant on the other side, and when we pull it over, that derivative of the constant, no matter with respect to whatever variable we take it to, is always going to zero out. But if there was a variable over on the right hand side and we didn't pull it over, it would affect the answer. So you should always go ahead and pull that over. That's why this says capital F. Remember, we've created those capital F functions that are equal to 0. That's got everything on the same side of the equation. So now I'm going to go through and I'm going to take the partial with respect to z. Well, the first term has no z's, so its partial derivative is 0. Second term has no z's, its partial with respect to z is 0. The third term has a z, so we're going to do the power rule on the z, and we're going to get negative 6yz squared. And the last term is a constant, so its derivative is also 0. In the denominator, we want the partial with respect to x. So we get 3x squared plus 3y squared. And we can go ahead and simplify this a little bit because I've got a negative there. And they can combine and just make this 6yz squared over 3x squared plus 3y squared. Ooh, there's one more thing we can do. We can cancel a 3 from everything. And we can make this 2yz squared over x squared plus y squared. And that is our partial derivative of x with respect to z. And we get that just by negating and flipping and doing partial derivatives on the capital F function. So let's try one more. Let's do the partial of z with respect to y. The partial of z with respect to y. So what we're actually going to do is the negative f sub y over f sub z. We're going to do this on the same exact function, and we've already calculated f sub z. We said that that was negative 6yz squared. So our numerator, we just need partial with respect to y. So if you look back at the capital F function we created where it was equal to 0, first term doesn't have y's, so its derivative is 0. Second term has a y squared, so we'll do power rule on there and we'll get 6xy. The third term has a linear y in it, so the derivative of the y drops off and we just get negative or minus 2z cubed. Last term's a constant, so its derivative is 0. And again, if we want to, we can combine those negatives and make this 6xy minus 2z cubed all over 6yz squared. Now, none of those terms has any variables in common. in the numerator, the first term has x's and y's, the second term has z's. So there's nothing common I can pull out in terms of variables, but they all do have a factor of 2 that we can cancel. So we can simplify this down to 3xy minus z cubed over 3yz squared. And that would be the partial of z with respect to y. So we can do implicit derivatives for these functions of several variables that are given to us implicitly. We always want to create that capital F function first by pulling everything over to one side of the equation. And then to get any implicit derivative, we just negate and flip, and we can do individual partial derivatives. And it's that simple. And then just try to clean it up a little bit, see if there's anything in common between all of your terms that you can cancel.